Good afternoon, and thank you for joining us. My name's Ross Peringuey. I'm looking after the product management portfolio for Delta Electronics, so our mission-critical infrastructure solutions products, power infrastructure, etc. And today, I'd like to really just highlight a topic. It looks like a long title, but really basic in principle. Looking at energy efficiency in the data center, and then striking the balance between reliability and ROI. And I think, based on some of the discussions that we've had today, a lot about where we're going from a green initiative perspective, how we're balancing these things from a sustainability perspective. And when we ask all of these questions, we also need to be cognizant of the fact that this has an effect on maybe the reliability of the system and the functioning of the system. So the idea here, trying to look from a little bit more of a balanced perspective at maybe something that's seen as more fundamental or legacy in a data center. It still makes a big impact going forward. So, optimizing for energy efficiency and striking the balance between reliability and return on investment. The agenda, we'd like to just have a quick look at the market trends. I think you've probably seen a lot of this today. Problem identification and focus, where we are going to specifically look in terms of what we want to discuss today. Then addressing energy consumption, addressing a growing power demand. This is what we see. Addressing system reliability and resilience, and here's where that difficult situation comes into play. And then addressing UPS storage topology and how that looks. So European data center trends, we see that the market size and investment at the moment around $65, $66 billion by 2027. Top 5 investors are contributing to around 60% of the overall investment received last year. In 2021, data centers that were opened or under construction added about 1.63 gigawatts of power. With many planned facilities, this power consumption expectation will go up to 2.51. It's a significant increase in the next 5 years. And some of the major growth contributors, of course, in the region include the UK, Germany, Ireland, the Netherlands, France, Sweden, Denmark, Poland. These are all big contributors to come in the next years. Here you can see a trend 2021 on the left, and then 3 scenarios in 10 years' time. We can see the trend in certain countries with a forecasted expansion between 4 and 9 gigawatts over the next 8 years. Here's the emissions reduction target, and I'm sure we've seen this several times today. But by 2030, we expect to adopt a 55% net emission reduction, and this target really paves the way for achieving climate neutrality by 2050. So what does that mean? Here we can see the trend coming down from the 90s to 2020 by 34%, and we want to extend that to 41% by 2030. So it's not good enough to just continue on the trajectory. There actually has to be a decrease or an increase in the capability and the capacity to reduce emissions. Energy consumption and trends. There's the scenario up to 2019. We see going up to 2030, if we carry on how the current trend ends up. We see, if we look at a worst-case scenario, that turning up to 160 terawatt-hours per annum by 2030. And this is just in Europe, data centers in Europe. We see the efficiency, which is the bottom line, curving down significantly. And this is an efficiency look or an efficiency perspective. And I think that's why I wanted to talk about it today. So let's have a look at the actual problem identification and the focus. And just paint a picture of where I want to zoom in a little bit for us today. So the facility type, we know it's hyperscale, it's co-location, it's enterprise data centers. But we want to look at the electrical infrastructure here, UPS systems, generators, transfer switches, and so on, in specific UPSs. This is my background. This is where I come from, so I want to talk a little bit more about that. We've spoken a little bit about the market size in terms of power capacity by 2027 in 5 years' time. And of course, the geographical region of interest here is Western Europe for us, the Nordics, Central and Eastern Europe as well. So power infrastructure is the UPS, and it's worth highlighting 2 things here. The first thing is that the purpose of a UPS in a data center infrastructure is, there's 2 reasons that we have it there. The first reason is to provide backup power. in the case of grid failure or a loss of incoming power, and there's a transition time before our backup generator kicks in or before the power mains returns, we see that this backup needs to be there in terms of battery storage and energy available for that short transition. But there's another very important reason why we have a UPS in our system, and that's for power conditioning. So typically on a utility network, and as you add new renewable sources of energy, we see that the grid stability can change. So we can see that there's these kinds of anomalies coming in, spikes, transients, sags, switching, RFI, interruptions, harmonic on the network. And these things need to be filtered out. We don't want our load exposed to this incoming power quality or these incoming power quality anomalies. So the industry, 7+ billion euros, will be spent on procuring UPSs over the next 5 years. And I think it's pertinent to understand the impact the technology has on the energy consumption, which is really the next topic, and the reason why they're so important in data center infrastructure. So we've discussed why they're important, but why is it important to look at a UPS when you're talking about large-scale energy consumption? The functioning of a UPS in online mode, and that's what we just had a look at, power coming in from the grid, conversion from AC to DC, and reconversion back to AC to supply a clean power output to the load. This process uses energy. So the efficiency of the system will determine how much power is utilized to perform those core functions that we just discussed. The more efficient the technology, the less the wasted energy in the system. And I heard somebody say a little while ago that, we can't look at these things anymore. We need to look forward at incorporating different thoughts and ideas around how we can change battery storage and peak shaving and so on and so forth. But let's not forget that a UPS is central to a data center. All the power comes through that device in order to service the load. That means the machine is online 24 hours a day, 365 days a year, always doing its job, and therefore always wasting energy. We should never forget about the impact that the UPS has on total power consumption, and what impact you can have by reducing a 0.5% efficiency. So addressing the energy consumption, how do we address that? We have brilliant UPS topology these days. We have the capability to have a modular system where we can really define and direct where the power consumption is happening, how much load the different modules in the UPS are taking. If it's a low load scenario, loading up some of the modules higher to a higher level, to an optimum running level, so that you can save on efficiencies there. This stuff is important. We can address the efficiency still in the total system so that we can reduce that power flowing through the machine all the time. What does that mean for return on investment? That small saving of, let's say, in this example over here, we're looking at maybe a 2 or 3% efficiency difference in running. What does that mean in running cost? First of all, in power consumption, when you have an efficiency difference of that size, 24 hours a day, 365 days a year, and remember the cooling that's attached to that. So if we have a UPS that's dissipating X amount of watts of heat, we need the cooling infrastructure behind that to then remove that excess heat. If we have a saving in the consumption of the UPS or the efficiency of the UPS, we have to have less cooling to be removed from the center as well. So there's a bigger impact than just the saving on the UPS efficiency. What does that translate to into kilowatt hours per year? And then what does that translate to in running cost, operational expenditure? Some systems with an efficiency difference of 2%, when we're talking about megawatt scale, can pay themselves off in 2 years, 2-year ROI, if we're looking at just the UPS equipment. Looking at the growing power demand. So typically, maybe a co-location facility on day one might not be utilizing the kind of capacity that it's designed for, right? Day one consumption is not always up to full load of where they expect the center to eventually operate. So here we have a capital-intensive spend where we're setting up infrastructure for a fully populated co-location facility. If we can reduce that up front and build the system in a way that it's scalable, we can save money here as well from a capital expenditure point of view. And once again, looking at that modular architecture, starting from something that can scale up from maybe 10 or 15% of the load requirements up to full load over the years, easy to expand. And at the same time, enjoying the efficiency of a system that's loaded optimally. Addressing the system reliability and resiliency. So while we're talking about all these things, we're saving energy, we're saving power, we can't sacrifice our redundancy in these kinds of facilities, and we can't sacrifice reliability of the system. That's not really an option. If anything, we need to be improving our redundancy, improving the reliability of the system while we're enjoying the benefits of energy consumption reduction and so on. And I think with these scalable and modular type solutions, we also see this benefit as well. Why? Because we have a resilient power path scenario where we have maybe 2 suppliers, we have multiple modules. These things can be interchanged and swapped. These can be expanded over time. And in doing this, we reduce the downtime to upgrade, first of all. And secondly, if there's some kind of failure in the system, there's redundancy built around it. So we have a mean time to repair that's very quick. The system keeps running, the module or the component swapped out, and there's redundancy in the system, and this is quick and this is efficient. And this saves on running expenses as well. Here you can see an example as well. Control modules, swappable, able to be changed. Static transfer switches, able to be changed online. So there's very little out of service time in the case of a component failure. Modules, of course, building up the total system capacity. There's built-in redundancy in the system itself. And then, of course, there's parallel systems. So you have vertical and horizontal redundancy as well in your systems built in. This all improving that mean time to repair. And then I think lastly, and it's just worth talking about, that storage topology. And we're all very familiar, I think, in the industry with lead-acid storage. This has been the legacy solution always. And I think in some markets, lithium technology has been adopted quickly, and it's going at a fast and rapid rate. In the European market, there seems to be an uptake by some of the major players quite quickly as well. And I think this is going to be something that evolves and that's going to be adopted more and more. So just some of the quick differences for interest's sake. These legacy lead-acid systems, larger power applications, of course, we're talking usually megawatt scale here. Weight is a big concern, right? Floor space. Specific energy, so how much power storage capacity can you pack into this area, basically volume. They're stable, it's a stable technology, it's well established, so people still prefer this as a very safe option. Lithium ion, this is fastest growing battery technology by far. Something that's not mentioned here, we've got LFP and NMC types generally in the market, and there's some differences between the two from a footprint perspective, from a lifespan perspective. I would say that energy utilization, how much of the capacity can you utilize? This is much better, number one. Number two, space saving is a big thing for these solutions. Weight is a big thing. We're saving a lot on the weight in the floor area. And this is why this is gaining traction. And I think lithium is seen as a greener technology when we compare it to lead. Here's a quick case study for interest's sake. 100 kilowatt load, 30 minutes backup time. On the left-hand side, you'll see the lead-acid scenario. Maybe you've got 2 UPS chassis for some redundancy there, and there you have 6 cabinets with 33.6 kilowatt-hour capacity each for lead-acid. If you compare that to a lithium solution, this would probably be more based on a NMC-type technology with a high discharge capability, which is in the market. There you're looking at 2 cabinets. So that's basically a third of the size, physically. And the weight you can see is around 1,800 kilograms versus 3,200. So a significant weight floor loading saving as well on the solutions. And this is why the popularity is increasing. And that brings us really to the end. Tried to keep it short and sweet. If there's any questions, I'd love for you to ask them. Thank you. Yes. There's a microphone coming there for you.
Thank you. Just there's been a lot of talk about sustainability today. Just wondering, is that factored in when sourcing lithium-ion batteries? Just a general query about that.
Yeah. Thank you. It's a good question. And I think what we've seen in the discussions today, the trend that we've seen is that it's all about the metrics and the measurements. So, we saw in some of the previous kind of presentations, there's no metrics, there's no data on water usage in a data center. There's very little when we look at when we look at PUE, this is a well-established thing, but when we start to look at actual energy consumption from renewable sources per time of day as a function of offset, we don't have clarity on that. And I think lithium batteries needs that same kind of metric for understanding. So you're quite right. It needs to be measured more carefully, I think. Yeah, good point. Any other questions? Thank you.